Yeah, let's start off. Camps on everyone. The last thing that we did, just had an YDCK introduction there. So let's go ahead. Like I keep saying, this whole chapter, the base is only one thing. If you can find your part difference, your job's done. So let's see. So we have the two slits. S1, S2, we have the screen here. So exactly from the center here, we are choosing a point y is equal to 0. So there is a point P somewhere here at a distance y. This angle is theta. So you know the story. We drop the perpendicular here, we drop the perpendicular here. This point becomes S1 dash and this point becomes S2 dash. So if I just exaggerate this, so if this is theta, this will be theta. This will be theta. This distance was d by 2. This distance was d by 2. That was the distance between the slits. This distance here will be d by 2 sine theta. This distance here is d by 2 sine theta. So you wanted to find the part difference, which is S2p minus S1p. Since the screen is very, very far, we can approximately assume this is S2 dash p minus S1 dash p, which is nothing but S2 dash S1 dash, which we can clearly see here. Delta x is nothing but d sine theta. This is the main theme. And remember, this is valid only if d is much, much greater than small d. That's your first assumption. D is much, much greater than small d. Clear with this. This is that approximation that we used. I mean, this is where it always starts, YDS. If something changes, this is where you have to come back every time. Clear? Then so this is S1, this is S2. So this is a point P at a distance y from here. This is capital D. So y is equal to 0 is the midpoint of that. Yeah, just give me a minute. My Wi-Fi just crashed, I guess. Yeah. So this is your main thing, the path difference. Now, if your distance d is much, much greater than y, that is, theta is small, this p is very close to the center. Just give me a minute. Hmm. Getting it? So if you take a point very close to the center, then your delta x, which is d sine theta, can be approximated to d tan theta. And tan theta can be written as dy by capital D. So we get delta x is dy by capital D. This is your approximate formula. This is what you will see in NCERT and everything. But remember, this is valid only if d is much, much greater than x. So be careful. But at an NCERT level, right, they won't go beyond this. And once you got this, you got your phase angle. Phase angle is simply 2 pi by lambda delta x. Once you got your phase angle, you get your intensity, which is nothing but I1 plus I2 plus 2 root I1 I2 cos phi. This is what I keep saying. Once you got your the path difference, you get everything. So all these things in the red box, those are the important ones. You can note it down. You will need that. Yeah. Now, again, we have our two standard cases, constructor and destructor interference. Now, if you open your NCERT or at a mains level, right, they will always stick to this dy by capital D. They will never go to the d sine theta stuff. Is my voice lagging? Yeah? No, right? Okay. So for constructor interference, again for d much much greater than y ka case, delta x is dy by capital D, which is equal to n lambda. So we get y is equal to n lambda capital D by small d. So for Maximus, n is equal to 0, y is equal to 0. This is called central maxima. Or central bright fringe. So keep this in mind. If someone asks you what is central maxima is when the path difference is 0. That is the meaning of central maxima. If you put n is equal to 1, we get y is equal to lambda capital D by small d. This is your first maxima. For destructive interference, again for d much greater than y, delta x is dy by capital D, and you're asking for minima, which is 2n plus 1 lambda by 2. So you will get here y is equal to 2 dy by 2n plus 1 capital D. Basically, the minimas will occur at if you put n is equal to 0. Wait, I did some mistake here. 2n plus 1 lambda capital D by 2 small d. Okay, so we get y is equal to lambda 2 by 2d. And so on. So all these are minimas. This is your first minima, this is your second minima, and so on. So here we define something called fringe width. Again, we use the symbol beta. This is the distance between two consecutive minimas or two consecutive maximas. Which you can clearly see is lambda capital D by small d. There, this is another formula which you need to remember. Fringe widths. So if you try to put this on a screen, how does it look like? Yeah. Now, if I try to put this on a screen, this is intensity. Let's say this is your y is equal to 0. So this is what you will notice. So this point here in the center, this is your y is equal to 0. This is your first minima. This is also a minima. So this distance between them, this is called central maxima or central bright fringe. And if you look at that length here, which is nothing but lambda capital D by small d, that will be the length of actually all the fringes. And if you look at this region here, you can see the fringes are uniformly placed. So this is the case where D is much greater than Y. Fringes are uniform and equally spaced, approximately. Now, if you to go too far from here, if you see this Y is large, the fringes won't be any more closer fringes spread out. And the fringe width will not be equal to lambda d by d anymore. The formula is not valid. If we take the central fringe width here, and if we take this angle to be alpha, so we define alpha is called angular fringe width. Basically, it's an angle subtended by the central fringe width at the center. Which is nothing but lambda d by small d by capital D. You can, since the fringes are smaller, you can approximately treat them like an arc. Clear with this? So the actual picture, right, would look something like this. I'll turn the page. There. So if you actually put a YDSC pattern, this is how it looks. You can see in the middle how the fringes are. So this is your central right fringe. So this is a position where y is equal to 0, and this width is there. This is lambda d by d. And you can clearly see here the fringes spread out. This is your y is equal to 0. So in the middle, you can see the fringes are equally spaced, and as you go to the right, they start spreading out. This is how the pattern would look. You just start to rotate it. This is in the x-axis. This I showed you in the y-axis. Angular fringe width. See, at a mains level, right, they always take that approximation d much greater than y. They'll never take that d sine theta one. They'll always take the d tan theta. So you have to be careful. Mains may won't have an issue, but advanced may they will poke around. And then if you just use the standard results without understanding how you got it, you will be gone. We will see. I'll show you how they can trap you. Clear with this? Any doubt so far? No. Type of slits. Case one, let's say if you use rectangular slits. So if you use rectangular slits, we get a cylindrical wavefront. And if you have this, so basically this is your S1, this is your S2. This is how you'll find the fringes. So it won't be a point, right? In 2D, it'll be like a complete thing. So this is the central right fringe. So when you say S2P minus S1P, P is the locus of all that points. Case 2, if you take circular holes, basically pinholes or circular slits. Now in HSC, the experiment they give us pinholes only. If they don't mention anything, we generally take it as pinholes. So here you get spherical wavefronts. Now here, remember what is the path difference? So delta x, your path difference is S2p minus S1p, which is equal to n lambda. That means for a given thing, let's say first maximize one lambda, which is constant. So if S2p minus S1p is constant, what is the locus? Hyperbola. Studied? S2p minus S1p is actually an hyperbola. So if you make pinholes and if you try to do this YDC experiment, the central will be a straight line because that will be 0, but the other fringes will become hyperbolic. Clear with this? The central will be a straight line though. So that is an HSA question. In YDC experiment, what is the shape of the fringes? Hyperbola. Options were like straight line, circle, parabola, hyperbola. There, technically, that is the whole theory of YDAC. I showed you this before. There. So those are the two sources in the liquid. There are like two slits, basically S1 and S2, right? And you can clearly see the interference pattern. I showed you this before. Now, if you're going to put a screen in front of it, there. So if you put a screen in front of it, you can clearly see the point where a minima touches the screen, that will be a dark spot. The point where the maxima touches the screen will be a bright fringe. So on that vertical screen, you can see the fringes actually. They're like, the black spots and the bright spots. You can see the fringe width. Able to visualize this? Now, if you increase the distance between them, see they made the distance between them bigger. Distance is small, distance is big. So what are you changing here? You're changing small d. What is the fringe width? Lambda capital D by small d, isn't it? So if you make the small d, so if you make that small d, bigger, then the fringe width should decrease. Can you see you got more fringes now? Basically, the fringe width is decreasing. Now, if you bring them closer, lambda capital D by small d is decreasing, so fringes are bigger. There you can see the bigger fringes. If you keep them even closer, there you can see there's only actually one big fringe. Yeah, that is how your fringe width changes. You can change it by changing wavelength. If you increase the frequency, wavelength decreases, you get more fringes.
हेलो, आज हम लोग करके देखेंगे यंग्स
This is also a
डबल स्लिट
decent video.
एक्सपेरिमेंट
You can do this at
और
home.
मतलब नेचर को हम लोग तो स्लिट के द्वारा बनाई होप आप देख
Look at this. This is how he made a slit. He took a stapler pin, and can you see the gap there? He kept one stapler pin in the middle. On either side of the stapler pin, there is a small holes. These are rectangular slits. Can you see how small the holes are? This is what I was saying. When I say D is very, very small, this is what we're talking about. So here, what is small d? Here, small d is the width of one stapler pin, isn't it? Making sense? Here, small d is the width of one stapler pin. So there, so we got a slits, two slits, rectangular slits with a gap of one width ka pin, and now he's going to hit this with a laser. Now, tell me one thing. Generally, if you take a sheet like this, and if there are two holes, and if you shine light, technically on the other side, how many light spots should you see on the wall? Two, right? That is the general feeling, isn't it? So if you take a cardboard, make two holes, and if you shine light, you should see two holes. right? And same thing. So if I hit this with a light, technically I should be looking at two light spots on the other side of the
आ
wall.
रहे होंगे इसे लाइट का मैं यूज करने वाला हूँ अभी इस एक्सपेरिमेंट को करने के लिए
So there he is just hitting it on a wall
ये
little
लेजर
far.
बीम
He's using a laser.
से पासर बीम को जो कि अभी डायरेक्ट लाइट बिना किसी स्लिट से पास होने के बाद
So without any slit, you can see the light just hits the wall. You can see one single spot, isn't it? Now if he passes through the slit,
डिस्टरबेंस का पैटर्न लेजर बीम को पास कराता हूँ उन दो स्लिट्स से ये पास हुआ ये स्लिट से इस कैमरे में देख पाना थोड़ा सा कठिन है लेकिन फिर भी अब स्लिट से पास होने के बाद
so from
आप सब
there
guess करेंगे
till the
कैसा
wall
स्क्रीन
is
पर
your capital D, isn't it? So capital D is the distance between the slits to that
पैटर्न
wall.
मिलना चाहिए
I think that's almost like 7-8 meters, 5-6 meters.
ये देखिए स्क्रीन पर बनने वाला पैटर्न
We expected to see two spots. But how many spots are we seeing? A lot of spots, isn't it? And can you see in the center? The fringes are equally spaced. And as you go to the left and right, they started spreading out. This is what Young's double slit experiment was. So Young's Maxwell, right? This is what he did with the experiment. And he simply showed, like, boss, if light was a particle, you should have seen two spots on the wall. But when you pass it through these two slits, right, the only waves behave like this. This is the nature of a waves. Since light is behaving like this, then light must be a wave. Such a simple experiment. And when he showed this, people didn't have any words like, there is no way you can, argue like light is a particle after seeing this. And people had to accept. And that is how he broke down that 150-year-old theory of Newton's corpuscular theory. Look at this thing. See, all that theory that I explained, right, is fine. You understood. But still, somewhere, if someone asks you, I took a paper, there are two holes, and if I shine light, the most common sense thing for you and me is there'll be two light spots. You ask any guy on the road, and he will say two light spots, including you and me. Now we know physics, so we might guess, oh, boss, YDC ho sakta hai, but the general notation is this only. But you can see how many spots are. That is definitely not two. That's like a lot. Making sense? So this is how a YDC looks. This you can actually try at home. I did this at home. The biggest problem in doing this, right, is to make such a thin slits. That was the biggest issue I faced. You will get a laser for 400 rupees or 300 rupees in Amazon. You'll get everything. Stapler. It's a pretty cheap experiment, right? So you should definitely try and see. It is fun. That is your YDC experiment. So it does happen. It is not our imagination. Clear with this. That's your entire theory of YDC. Let's see some problems. We have two slits. Capital D, small d, S1, S2. So let's say capital D is 4 meters. Small d is 2 mm. Wavelength lambda is 6,000 angstroms. I'll keep the data almost same. And let's say you're sending parallel beam here. Basically, the light is in phase when it is coming. This is your y is equal to 0. There is a point P here at a distance y. Find the intensity at point P. I is the intensity of the sources. First case that y is 2 millimeters. Second case y is 3 meters. Let's see. The first one is a proper mains question. Second one becomes an advanced question. Let's see one. I'll help you with 1C. Let's see the first case. In the first case, D is much greater than Y. So that is the first thing you need to always ask yourself. Mains you won't have an issue. Advanced you will get trapped. So if D is much greater than Y, then I can use my approximate formula. Delta X is equal to dy by capital D. D is 2 mm, 2 into 10 power minus 3. Y is 2 mm, 2 into 10 power minus 3. Capital D is 4 meters. So this is 10 power minus 6 meters. Phase angle will be 2 pi by lambda. Lambda is 6000 angstrom, 6000 into 10 power minus 10 into 10 power minus 6. That would be how much? Pi by 3, 10 pi by 3. And remember, phase angle is always between 0 to 2 pi. So this can be written as 4 pi, 2 pi plus 4 pi by 3. So basically this is 4 pi by 3. And therefore the intensity will be I1 plus I2 plus 2 root I1 I2 cos phi, or I can directly use 4i cos square phi by 2 cos 4 pi by 3, which is minus half. So that is I. Clear with this. We used everything. Delta X, phase difference, intensity, everything. The second one. Here Y is comparable to D. Means your formula is gone. You can't use that d pi by D. But you can still use this formula. So delta X is d sine theta, which is equal to dy by root over d square plus y square. This is still right. For small angles, we made that sine theta is equal to tan theta. That was the problem. So this was 2 into 10 power minus 3. Y is 3 meters by root over 3 square plus 4 square. That would be 6 by 5 into 10 power minus 3. Same story. Once you got that, you are done. Phase angle will be 6 into 10 power minus 7. 6 by 5 into 10 power minus 3. 6 goes off, 2 by 5. 10 power 4. I think this will be 0 degrees only, isn't it? That will be some 2 pi ka value only. So intensity at 4p will be 4i cos square 5 by 2. Same formula. If intensities are same, you can use this directly, which is 4i. It's a maximum. Clear how we did this? So you just have to be careful. Is y small, y big? Appropriately use the formula and then you're done. You get everything. Any doubts on this? Next thing. Let's say this is 4 meters. This is S1, this is S2. This is point P. P is exactly in front of this thing. And this is 3 meters. Find the intensity at point P. So just to give an idea here, delta X is not equal to d sine theta anymore. Why? D is comparable to capital D. You can't use any of the formulas. This is not YDSA. then you have to go back to the whole school. What is the path difference? S2P minus S1P. We shadow made it mm, I guess. ठीक है. See, again, go back to the story. What do you want to find? Path difference. So delta x is S2P minus S1P. I gave you good numbers. S2P is 5. S1P is 4. So path difference is 1 meter. Phase angle 2 pi by lambda delta x. Maybe I should have given 1 mm. Okay. This is 2 pi 6 into 10 power minus 7 into 1. Still it won't make a big difference. This would be pi by 3 into 10 power 7. So I think this will turn out to be 4 pi by 3. No? Or 2 pi by 3. Something. Or, it should be one of them. You can figure it out from there. It will be something like 3.3333, something of that sort, isn't it? Then you will get end some pi by 3. So check it out, that thing. So then once you got that, then your job is done. Intensity is 4i cos square 5 by 2. This would be 4i, that will be cos 2 pi by 3, so that will be 1 by 2 cos square. That will be I. Clear with this? Check it out, that thing. If it is pi by 3, then we have a problem. 2 pi by 3, 4 pi by 3, 2 pi by 3 is also a problem. I think it is 4 pi by 3. But got what to do, no? That is like 1 million by 3. Shit. So you can actually write that thing as 99999 thing. Then you'll be left with 1 pi plus pi by 3. I think it's 4 pi by 3. Anyway, you got that. Next one. You're getting how I'm breaking all that thing. So if D is, comparable to small d, your whole YDIC is gone. Then you can't use anything. You have to go back to the basics. D is 2 millimeters. Lambda is 6,000 angstroms. Find the position of tenth maxima or 10th bright fringe. Thousandth maxima. 10,000th maxima. Let's see how will you approach this. This is a good one. Yes, I can ask as a more than one choice question in advance also. All three. If I ask you just the first one, it's a proper mains level question. Think, I'll give 3 minutes. First is easy. Right, Anna. Yeah. First is easy, everyone. Get the second. Just give it a try. See. So when you get this kind of questions, right? When you see numbers like second maxima, fourth maxima, 10th maxima is also fine. The moment you hear numbers like 100th maxima, 200th maxima, be very suspicious. Something is wrong. Let's look at the first one. Delta x is dy by capital D. This is valid only when d is much greater than y. So just let me use this. I don't need this actually. I need fringe width. Fringe width is lambda capital D by small d. This is valid only when d is much greater than d. This is 6 into 10 power minus 7. Capital D is 2 meters. This is 6 into 10 power minus 4 meters. So for the 10th fringe, it will be 10 into 6 into 10 power minus 4 meters or 6 mm. And you can clearly see D is much greater than 6 mm. So yeah, my approximation is right. But when you do it the same thing for the B1, 1000th fringe, this becomes 10 power 3 into 6 into 10 power minus 4. This becomes 0.6 meters. So here this is comparable. So y, which is 0.6 meters, is comparable to d. So your basic assumption is wrong. Then you go back to the story again. So then how to do the bth one? So delta x is d sine theta. This is right. This does not matter how big is y. So this is dy by root over d square plus y square. And you said which maxima? 1000th maxima. So it is 1000 lambda. Isn't it? N lambda. N is 1000. Because it's the 1000th maximum. D is 2 into 10 power minus 3. Y I don't know. Root over D is 4 plus y square. 1000 lambda is the... Hmm. Hmm. I missed something here. No. And yeah, that looks fine. No, something is messed up. 6000, no? Hmm. How much will that be? By root over 4 plus y square is equal to 0.3. Hmm. This will be 100 y square is equal to 9 into 4 plus y square. This y will be 6 by root over 91. That's your answer. Clear this. This would be an advanced question. Yeah, some of you got it. All clear how we did this? What about the 10,000th one? Now, again, remember I taught you how to count the maximas and minimas. If you go to that, so if you go straight to the center, the path difference is 0. But if you go parallelly at infinity, the path difference here delta x will tend to d. D is the distance between them. So if delta x is equal to d at infinity, which is equal to n lambda, so this is 2 into 10 power minus 3, n into 6 into 10 power minus 7, we will get n tending to 1/3 of 10 power 4, 3333.333. That means here you'll get n tending to 3033.333. Here will be n tending to minus 3033.333. There are only 3333 maximas on the top and the bottom. 10,000th maxima does not exist. You cannot just multiply. So when you see huge numbers, always check whether it exists or not. And they can ask you another question. How many maximas are there? In total, you have 6,667 maximas are present. Clear with this? This is how you can play around. So be very suspicious when the numbers exceed, right? 30, 40, 50, 100th fringe. It's definitely suspicious. Matlab, generally means they'll stick to something below 10. So you won't have a problem. Clear with this? Because even if you look at this thing, right, we got how much here? This is 0.6. This is somewhat close to 0.6, isn't it? It's not really outrageously very far. If the denominator is root 100, you would have got something like 0.6 only. So even a 1000th fringe is still in a reasonable range. It's not really gone. So even if they ask you like 20 or 30th fringe, it still is in a visible, in a reasonable distance. All clear with this? Let's say we have a source here. That means the source is not in the center anymore. Let this distance be x. Let this distance be d1. Let this d2 distance be d2. There's a point P here at a distance y. X and y are much, much smaller than d1 and d2. Both are small. Okay, so the source is not on the center anymore. Find the position of central maxima and find the intensity at point P. I gave everything in variables. You can understand what is central maxima, the point where delta x becomes 0. These are advanced stuff. There's really not, YDS is really not that tough. Like I keep saying, it's always about finding delta x. So you see few models. I think in total, there might be like 4 to 5 models. You know them, you can handle most of them. How do we handle this? Take small d, na? Let's see. Now, again, don't think about that source and all. End of the day, what do you want to find? You want to find delta x. So let's see from the slits ka perspective. Now, if you ask the slits, what is S? Tell me one thing, just look at the slits ka perspective. Forget about YDS and everything. If you ask the slits P and if you ask the slits S, do slits differentiate between S and P? Whatever you do on the right hand side, you can do the same thing on the left hand side, isn't it? For the two slits, P is a point, S is a point. That means I can play the same story here again. So we will draw a line like this. We'll extend the line. This angle is theta. We will drop a perpendicular. We will drop a perpendicular. We will say this is S1 dash. We will say this is S2 dash. This angle will be theta, and this will be d by 2 sine theta. Same story we will say. Then we will say here the path difference, delta x, you want S2s minus S1s, which can be approximately written as S2 dash p minus S1 dash S2 dash S minus S1 dash S, which is S2 dash S1 dash. So delta x will be d sine theta. Since it is very small, you can write this thing as d tan theta, which is nothing but dx by d1. Isn't that the same story, which you're going to write on the right-hand side? So now here, when I write the path difference, exactly what is your path difference? S, S2, P minus S, S1, P. Isn't this the path difference? You're taking the light rays from S to point P. One is going through the source and S1, and one is going through the S2, isn't it? So this can be written as SS2 plus S2P minus SS1 plus S1P. This is nothing but SS2 minus SS1 plus S2P minus S1 minus S1P. This is nothing but dx by d1 on the left hand side. This is nothing but dy by d2 on the right hand side. Make sense? So even if your source is, not in the central position, you can still work it out. Any doubts on what you did? Once you got here, like I said, your job's done. So your path difference delta x, dx by d1 plus dy by d2. For central maxima, someone asks you central maxima means delta x is 0. This will give you y is equal to minus x d2 by d1. The minus sign indicates it is actually on the lower side. Next thing, you want intensity at point P. So once you got delta x, you get the phase angle phi is equal to 2 pi by delta x into this. Since the intensities are same, IP is equal to 4i cos square phi by 2. Numbers are given, you can substitute. Are you clear what we did? So if the source is not equidistant, it is somewhat shifted. This is how you play around. It's like you're doing YDCK approximation on both the sides. Is that making sense? You want to find distance from S to S1 and S to S2, which is same as S2S and S1S. For the two slits, the source and the object, right? If the point P really won't make a difference, the approximations work. Yeah, as long as the x and y are small. Yeah, you can also do binomial approximation. But end of the day, you'll get the same thing. All clear with this? Let's say we got a screen here, which is connected to a spring here. And let's say this is oscillating in SHM here. Initially, this is the mean position x is equal to 0. This is S1, this is S2, this is distance t. Point P is your first maxima. Now, if the screen starts oscillating, the distance between the screen and the slits also will change. That means the position of first maximum will keep changing. Find the velocity of point P. So P is not a fixed point. P is the position of first maxima. If the screen moves, the maxima ka position also changes. Find velocity of P at time t. Let's see. After some time t, the distance between them becomes d plus x. Now, if you look at your first maxima here, understand one thing. Not only the screen is moving, if you look at the coordinates here, this will be your fringe width, which is lambda capital D, but D ka place mein you have d plus x by small d. So the coordinates of point P will be d plus x, comma, lambda by small d plus x. So the point P is going up and down also. It is also going left and right also. So the position vector of point P will be d plus x I cap plus lambda by d plus x j cap. Velocity of point P, differentiate this. Dx by dt I cap, lambda by d dx by dt j cap. This is I cap plus lambda by d j cap. Dx by dt is a omega cos omega t. Check. So be careful. The P is also going left and right and up and down. It's actually going at an angle. Clear? Take a break. Come back by 9:40. Come back in 5 minutes. Any doubts so far? Let's see the next one. You have a double YDSA. Let's say this is D1. Let's say this is D2. Distance between them is D. The distance between them is 2D. So here we are getting a parallel beam of light. S1, S2, intensity I and intensity I. So what happens here? The light falls on this. This will become a new source S3. This will become a new source S4. And these two again will have a YDSA. Find the intensity of the central maxima. Let's see. Yeah, this thing looks scary. It is not. So let's take this thing as S3 and S4. Luckily, both are identical. So if I just do for one guy, the other one is taken care of. So for the first one, for S3, what is the part difference? Part difference is D. Y ka place mein you have another D by D1. That's your part difference. So what is the phase angle? 2 pi by lambda D square by D1. Then what is the intensity of I3? Since I1, S1, S2 have same intensity, it is 4i cos square 5i2. Similarly, this will be the same thing for I4 also. Now S3, S4, central maxima, right? for S3 I4, then intensity of the central maxima is Imax, which is 4 times I3. So that will be 16 times I cos square 5 by 2, which is pi by lambda d square by d1. Clear with that? The question my d2 would have come if you asked at point P. Suppose if you have taken a point P at a distance y, then for S4, S3, then your path difference delta x would have been 2d. So d का place में 2d we have and y by d2. This should give you another phase angle phi dash, which is 2 pi by lambda delta x. Then intensity at point P would have been 4 I3 cos square phi dash by 2. Are you getting it? Basically, the first YDC, right, will only take care of intensity I3. Na? Once you got that intensity I3, forget about S1 and S2. So now you got a new YDC experiment where S3, S4 intensity is I3, and then you just do your regular YDC again. Are you clear with us? And since luckily S3, S4 are symmetrical, your life becomes easy. If they're not symmetrical, then it's a little mess. You have to do it 2 times. Clear the steps? There you can see, like, you just keep playing like that. Let's see some standard questions also at a mains level, right? There are few standard models. They will just stick to them. So let's see them also. I'll keep all of them together so that it'll be easy. This is intensity I and this intensity 4I. Find intensity at point P. If nothing is mentioned, remember it's your regular YDSC. Find the position where the fringes overlap. Let's see. The first one is easy. First thing, the phase difference delta x is dy by capital D lambda by 3. phase angle is 2 pi by lambda delta x, which is 2 pi by 3. Therefore, intensity at point P will be I1 plus I2 plus 2 root I1 I2 cos phi. This will be 3i. Easy. Direct formula substitution. This is the type of mains questions you get. The second one, the fringe width beta red, let it be, let's say the nth red fringe overlaps with the n2 the violet fringe. So this is a lambda red capital D by D. Beta violet, let it be NV lambda V D by T. When they overlap, both should be at the same distance. And we get NR lambda R is equal to NV lambda V. So NR by NV will be 4:7. The meaning of this is the fourth red fringe overlaps with the seventh violet fringe. And so on. 8th will overlap with 14th and so on. So the first fringe to overlap is 4 and 7. Clear with this? Easy? Any doubts on this? Next one. We have two identical bulbs. Intensity I1 and I2. Find the intensity at central maximum. Let's see. Now, if you try to this thing, two coherent sources are never, two light bulbs are never coherent. Maybe I should say y is equal to 0. Basically, this phase angle phi varies with time. So if you look at your intensity का formula, I resultant I1 plus I2 plus 2 root I1 I2 cos phi. The cos phi ka average value will be how much? If the phi is varying continuously, average of cos phi is 0. So this term becomes 0. So we get the intensity will be I1 plus I2. This is what is actually happening in your room right now. When you switch on two bulbs, there is no interference pattern. The entire room will be uniformly illuminated. So there will be no interference pattern and the whole screen will have an intensity of I1 plus I2. The answer is I1 plus I2. So these are incoherent sources. So if they use incoherent sources, what is intensity? I1 plus I2, just add them. So instead of light, if alpha particles are used. If alpha particles are accelerated by voltage V and then used in YDC experiment, find the fringe width. Normally exam they'll say like this. If the voltage becomes 4 times, what happens to the fringe width? Let's see. First thing, your de Broglie wavelength. That's where you get this from. We have done something like this where magnetic force and proton and an alpha particle are projected with same potential, same electric field, same velocity, same momentum. Find the ratio of radius. So this will be h by mv, which can be written as h by root over 2 into mass into kinetic energy. This can be written as root over 2 into mass into charge into voltage. So it's actually proportional to 1 by root voltage. And then you're done. So once you got lambda from here, lambda capital D by small d. Clear that? So in 2006, IEEE, there is a question like this. If electrons are used in YDSC instead of light, what happens? There are 4 options. The fringe width will increase, fringe width will decrease. There'll be no interference. There'll be no, there is no interference. ऐसा कुछ options था. Me being a super intelligent, since we can't see electrons, there is no interference. Therefore, no interference. I marked it. So then it's like just because you can't see doesn't mean it is not there. So that is the logic I used. I got it wrong though, but yeah, we do dumb things. Next thing. What if the light is coming at an angle? Alpha is small. Find the position of central maximum. Let's see. So let's say there is a point P somewhere here. Now from here, if this is your S2, this is your S1, if you drop a perpendicular, this will be your extra path difference, which will be, if that is alpha, this is alpha, that will be d sine alpha. So now when you here write the path difference, so that means the light rays which is coming to S1 is already traveling a little more. So this is S2P minus S1P, but this S1P already traveled extra distance d sine alpha. Make sense? Okay, that's how you find your path difference. So previously S1, S2, the light rays used to be equal because they're parallel. Now they're not anymore. So this is S2P minus S1P minus d sine alpha. And what is this? This is nothing but dy by capital D. And what do you want? Central maxima, then 0. If you want first maxima, 1 lambda, and so on. Y is equal to d sine alpha. Clear? So S1 is traveling more. So the maximum will shift little, upwards. Next thing, what happens if you have slits of different size? Let's say we have slits of, let's say, L, and width is D or W. Let's say this is NL, width is same. Let's say length is same, but the width is NW. So this will have intensity I, this will have intensity Ni, this will have intensity Ni. So basically the intensity is proportional to the area of the slit. Think about it. The bigger the area, more light will enter. If more light enters, the slit will have more power. Getting it? Don't get confused. There are two different types of intensity here. Due to a point source, the intensity is power by area. Okay? But when you take a hole, the light is coming from somewhere. So power of this hole is intensity into area of this slit, isn't it? How much power you're receiving will depend on the area of the hole. If you have a big window, you get more light. If you get small window, you get less light. So intensity is proportional to the area of the slit. So maybe I should have written like this. So power of the slit. Power received by slit is proportional to area of the slit. Since you have more power, you have more intensity. That will be different. If they use circular slits, or circular holes, if this is R and this is NR, then the intensity, if this is I, then this is N square I. So be careful about the shapes. But generally in the exam, the question they'll say the width of the slit is doubled. Getting it? So for circular thing, they'll say radius. If they say width, they're talking about rectangles only. If the ratio of width of the slits is 4:1. This is how you change the intensity of the sources, I max by I minimum. Get this? Like I said, these all are main level questions. Generally, mains they won't go beyond all the standard models. All that, d sine theta, double YDSC, source is not in the center, all that's the main, that's all advanced stuff. This was easy. So I1 by I2 will be 4:1, because if the width is double, then area will double. So this is root I1 plus root I2 whole square. So you know your formulas. Root I1 minus root I2 whole square. 9:1. Clear? If the whole setup is immersed in a liquid, what happens to the fringe width? So initially it is in vacuum. Now you took the whole setup and just dipped it in the liquid. What will happen to the fringe width? Increase, decrease, remain same, depends on the refractor index, blah, 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 something like that. Remember, whenever you put into a medium, frequency remains same. So C is equal to F lambda, C is proportional to lambda. So lambda for medium will be lambda for vacuum by mu. Wavelength decreases. So the new fringe width will be lambda medium capital D by small d, which is 1 by mu lambda vacuum capital D by small d. So it decreases. Clear with that? If the intensity of one slit is increased, what happens to the intensity on the screen? Options will be like intensity will increase everywhere, intensity will decrease everywhere, intensity will increase at some places, it will decrease at some places, right? So something of that sort. What happens? Initially, both are same. One of the intensity is increased. See what happens. So if I1 is equal to I2, your Imax will be 4I, your I minimum will be 0. If your I1 is equal to I, and if your I2 is greater than I, your Imax will definitely be greater than 4I, and your I minimum also will be greater than 0. You will not get a dark spot. If I1 is not equal to I2, you will not find a dark fringe. That means what? Bright spots become brighter, dark spots also become brighter. You're getting it? So bright and dark fringes, the intensity increases at both the places. Basically, intensity increases everywhere. Previously, dark fringes used to be 0, but now even that will increase. Clear with this? What if you use white light in the experiment instead of a monochromatic light? So what happens, right? The whole thing gets mixed up because see, white light has all intensities, all wavelengths basically. So at some places, the red ka dark spot may there'll be violet, violet ka dark spot may there'll be something else, and so on. But there's one spot, So white light has all wavelengths, so all the fringes will overlap. Right? We don't see any proper pattern. The central fringe will be white because that is only the one place where for all the wavelengths at the central maxima. Since it is central maxima, for all lambda, it is central maxima. Means it is a red ka dark bright spot, yellow ka bright spot, violet ka bright spot. If everything is a bright spot, so that will be white. And remaining places you can see there is no dark fringe. The whole pattern will get messed up. This thing is very useful. Remember that experiment I showed you just now? You can see how small is that gap, right? It is a width of one, one stapler pin. Now you tell me if this is S1 and this is S2 and the wall is so far, do you really think you can find y is equal to 0, the central cup position? You think it is really that easy to measure exactly the middle of that thing? So normally when people do the experiment, you know what they do? First they take this YDC experiment, they shine white light. Then you get a white spot. That is your central maxima. No? So now you mark that point as y is equal to 0. Then you do monochromatic light and then you do the experiment. So this is an important theoretical question. So how do you locate a central maxima? Use white light. This is useful to locate the position of central maxima. Even though we know mechanically it is in the between the slits, the distance between the slits is in millimeters and the distance is 2 to 3 meters, you can't exactly locate it. So this is the best thing to do. Shine white light and the point where you get a white spot is your central maxima. That is one. They can ask one more question. Just after the central bright fringe, what is the color that you can see? You can clearly see it is more reddish. Again, the reason when the fringes form, what is the first color? What is the smallest fringe you have? Violet, isn't it? Lambda violet is around 4,000 angstroms. That is the smallest fringe. Lambda red is 7,000. That is the biggest one. So when the fringes form, this is how they will be. The red will be big and the violet will be small. So up to this region, all the wavelengths will be there. So this will be a white fringe. So after this, blue is missing, isn't it? Then you will see yellow, then everything red will start dominating. So this looks more reddish. I won't say perfectly red. Blue will be missing. So it will be more towards red and yellow color, like you can see here. You can see it's getting more reddish. So just after the white fringe, that what you see is a reddish color. Clear with this. And this is what happens if you send white light. Extension of that question. This is S1, this is S2. Let's say we have a point P exactly in front of S1. And let's say you're sending white light. Basically all wavelengths. So this question now is called missing wavelengths. Find the missing wavelengths at point P. That is how they'll ask you. If you send all wavelengths through the slits, there will be some wavelengths which are missing at point P. So what it simply means is certain wavelengths will form a destructive interference at point P. What are those wavelengths? Find lambda for which they form a dark fringe at point P. So they will not write like this. They'll simply find the missing wavelengths. So you should know what is the terminology for that. Get this? Easy one. So since it is exactly at point P, so what is this distance? D by 2, na? So basically y is d by 2. Path difference will be dy by capital D, which is d square by 2 capital D. You want a dark fringe. So 2n plus 1 lambda by 2. Therefore, lambda will be d square by 2n plus 1 into capital D. So the missing wavelengths will be lambda square by d, lambda square by 3d, lambda square by 5d, and so on. Easy? There, they can keep on asking more and more, but I think this roughly this 10 questions, right? These are like standard models. You'll be able to handle the most. Clear? I kept all this 10 together. Any doubts on this? Next one. We got a lens here, focal length 20 centimeters, object 30 centimeters. Then what you did, you cut the lens. And separated. by 2 centimeters. Object is still there, 30 centimeters. 1 centimeter, 1 centimeter. You kept a screen here, 2.6 meters. Find the fringe width. I assume light does not go from the middle. Easy one. We are combining ray optics with this. Yeah, in ray optics we did another equation. We cut it and then we combined it. You can play like that also. That was even much better one. The lens is, 2 centimeters is removed from the middle and then the lenses are joined. Here I just cut it and separated them. I didn't do any cutting, that. This actually kind of becomes easy. Let's see. ले लेना lambda. Let's see. This thing. So let's just set the image. So if you think about this, it really doesn't matter. When you cut it, the principal axis remains the same. So this is still the principal axis. Object is here at a height of 1 centimeter. Focal length is 20 centimeters. So 1 by V minus 1 by U is minus 30 is 1 by 20. We get V is 60 centimeters. Magnification is V by U, which is 60 by minus 30. It's minus 2. That means this image will form somewhere here at a height of 2 centimeters inverted, and this is 60 centimeters far. So if I take this upper one, I'll get an image here. Let's call it I1. That would be 3 centimeters in total, because 2 from the principal axis and this thing. The lower one will also get an image. That will be somewhere here. I2, this also will be 3 centimeter. And this distance will be 60 centimeter and this will be 2 meter. You're done. So small d 6 centimeters, capital D is 2 meters. Fringe width is lambda capital D by small d. Got this? Next thing. Now this is like kind of like an experiment and also a question. Lloyd's mirror. So we have a mirror. And we have a screen. This is y is equal to 0. This is your source at a distance x. Find the position of first maxima. The image will be the second source. Let's see. What is the catch here? One thing is clear. So if you choose a point P here, so light goes directly to here. The other one hits the mirror and bounces off. Basically, it behaves like this is the light source. But there is a thing. Whenever a light ray hits a mirror, there is a phase shift of pi. So this image behaves as if the light ray from the image behaves as if it has traveled extra lambda by 2. So now the path difference delta x will be, now if you look at this, it has become like this. So we have two sources S and I, and this is point P. Small d will be 2x because this also will be x. Didn't I give you capital D? I should have given capital D. So here and this guy will have an extra lambda by 2. So S2 का place में we have I. So delta x will be IP, but IP also traveled extra lambda by 2 minus SP. That will be IP minus SP plus lambda by 2. And you know what is IP minus SP? dy by capital D. Now here, if you notice something, if you put y is equal to 0, delta x is not 0, delta x is lambda by 2. This is your central minima. There is no central maxima here. So that means below y is equal to 0, there is no pattern. So if you look at that screen, this position here is actually a dark spot. And there is no interference below this. There's no light rays only, no? All light rays are going up only. So below y is equal to 0, there is no interference. That means if you look at the pattern here, this is your first maxima, which will be at a distance of lambda d by 2 small d. So the whole pattern will shift by half fringe width. Then again, you get your first minima here. So y is equal to 0 is the central minima. Then again, the brightness will increase and then again will decrease. And then you get a second minima and so on. So the fringe width will remain same. Only the whole pattern must have shifted up. And there is no central maxima here. Clear with this? So the first maxima you will find in the place of the first minima in a regular YDSA. All clear with this? Yeah, that's a bit about it. So next class when we catch up, we'll continue from here. We have few more models on this YDSC, not much. Another 2 experiments are there, biprism experiment and Quincke's tube. And then we will go ahead with something called path difference and all that stuff. I think mostly next class we will wrap up almost 90%, maybe a little might spill over. So next Monday, mostly I think in the maybe another half an hour, 45 minutes, we'll wrap up the chapter and then we'll start with modern physics. So we have in this diffraction and polarization, which are again mains only. This is not there for advanced. So we will do that in the end. But again, we have done almost like 16 questions, but the 14th one has 10 parts in it. So make sure to go through this. Again, not a tough chapter. You need to see few models. You need to do a little practice. And all the questions, if we see the theme is same. Somehow find delta x, then things fall in place. So do start solving. Mostly after Friday, you'll be able to handle most of the questions. So, okay, with that, we'll wrap up for that day. I'll see you guys again Friday at the same time. So, and do remember there's a test on until Friday night. So make sure to give it. People are asking for extensions and all. People are like, sir, Saturday we have that.